Good day everyone, this is Earl Royce Hugo and today I'm going to demonstrate the operations involved in a binary search tree using this application that I created using C# and Windows Forms in Visual Studio. Let's dive right into it. Alright, so this is my application interface. As you can see, I have a placeholder here for a 15-node perfect binary tree. The code can actually handle more nodes than what is displayed. So this is just for this demo purposes. This is just a status box, and these are the different buttons that I use to call the methods of my tree. Okay. Alright, so this is my main code. The main form actually just houses the button events that call the tree methods. So I won't be diving into all of that. So let's take a look at my implementation. This is how I defined the node, a node of a tree. So I have a pointer to the parent node, which allows for easy traversal. Value is the actual value of the node. The count here is how I manage duplicates. So my duplicates are inserted on the same node, but the count is just incremented. And then these are the pointers to the left and right nodes. Okay, so let's look at the tree. So this is how my tree is implemented. So alright, so I have the different methods here that are called by each button. So for the insert, what I do is recursive insert. So it tries to find where to put the value. If the value is less than the current node, then it goes to the left, and if it's greater than the current node, then it goes to the right. All right, deleting. Now for deleting, in my opinion, this is probably the most complex method of the tree, because there are several cases that needed to be considered. So if we are deleting a node with no child, we just free that. If we are deleting a node with one child node, then we perform a different function, and also different for a node with two children. So for two children, we swap the successor and the node that we are deleting, but then we also need to consider if the successor has one child or if it has no child. So we'll see that in action later. Alright, so for the minimum, we just go to the left until we find the leaf node, and that is the minimum. For the maximum, we just traverse to the right until we find the leaf node, and that is our maximum. For the successor, what we do here is look for the minimum in the right subtree. Unless there's no right subtree, then my program looks for it in the parent. For the predecessor, what we're doing is looking for the maximum in the left subtree. Again, if there's no left subtree, we just look for the predecessor in the parent. Okay, so my search and print methods are actually called in the main form, but basically to search, I attempt to go to the node. So if I can get to the node, then it's there. If not, then it's not there. The value is not there. And for printing, what I do is I do an Inorder recursion so that I can print the values in increasing order. Alright, so let's perform some operations on this existing tree. So if we try to insert 14, it will recursively try to find where to go until it gets to the left of 15. If we try to insert a duplicate like 37, it goes to the same node but updates the counter. Deleting chooses the appropriate case. So deleting 6 is a leaf node delete, so it's just deleted. 10, deleting 10 is a two-child delete, so 10 is replaced by its successor, which is 14. Okay, minimum traverses to the left until it finds a null, so we have 8. Maximum traverses to the right until we get to 50. For the successor, the program looks at the minimum of the right subtree, so the successor of 25 is 37, while for the predecessor, it looks for the maximum of the left subtree, and in this case, it's 15. Searching, my code attempts to go to the node. If it can get there, then it's there, but if it can't, then it's not. Alright, displaying in order displays all the values in increasing order as shown here, and resetting the tree will reset the tree. So thank you.